I know for most of you it's been a minute since you've looked at Cartesian coordinates, so let's go over how to graph things on coordinates real quick. So the first thing you want to do is you want to label the axis, right? So to label the axis, so this is the x-axis down here, and this is the y-axis. And then when you have these points, per convention, the first number always tells you the x-axis, and then the second number tells you the y-axis. So that means that if we then try to graph some of these, right? Let's say we try to graph this one, A, it would go minus, so this is 0, minus 6 on the x-axis, and then up 3 on the y-axis. So your point would be right there. Let's go change the color just so that you can follow me along. Let's do this in green. So if you wanted to do E, for example, E would be you go over 3 and then you go up 4. And so E would be right there. And then for, because all good things come in threes, if you wanted to do I, for example, that would go over 7 and then down 2 on the y-axis. So that would go right here. Now that we covered that, we need to talk for a second about variables. So we've talked about variables in the past. We've talked about the independent variables and the dependent variables. The independent variable is independent of the experiment. So that's the variable that you set up. The dependent variable depends on the experiment. So that's the outcome. So the independent variable is part of the setup. That's you decide that. And that traditionally gets put on the x-axis, whereas the dependent variable is part of the outcome. It's the thing you measure, and it goes on the y-axis. So y-axis being here, x-axis being that. So if you had a chart where you're graphing time versus survivors on this graph, and let's just say for sake of argument you have time 0, 1, 2, 3, and 4, and you at time 0 you have 10 survivors, at time 1 you have 8 survivors, 5 survivors, 3 and 0 survivors. The way you would graph this is put the pointer options here again, and let's make this purple. Time and generation, that would be your independent variable, right? Because that's the time just passes without you having anything to do with that, right? So this would be your x-axis versus the generation part. This would be graphed on the y-axis. So if you had to write these things like this, that first point would be 0, comma 10, right? So 0, comma 10, 0 and 10. So this would be where the first point would be. 1, 8 would be 1 over and 8 up. 2, 5 would be 2 over and 5 up. 3, 3 would be 3 over and 3 up, and 4, 0 would be 4 over and no up. And then if you would combine these points that you just drew into a graph, this is the graph you would get. Okay, so far so good. Granted, semi-log paper is a little more scary looking than the Cartesian coordinates, but let me explain to you why there is a need for that kind of graph paper. So let's say you're trying to graph a generation of bacteria, for example. So here's the offspring, and this is something that happens in biology quite a bit, right? So the first time around, at time 0, you have one bacterium. Time point 1, you have 2, then you have 4, 8, 16, 32, and 64. So they double each time, right? And this is something that, could easily happens all the time when bacteria duplicate. So let's try to graph this, and let's graph it first on the Cartesian coordinate, because that's the thing that we at this point already know. So let's give ourselves a pen. So 0, 1, again, this is on the x-axis, this goes on the y-axis, because this is time. It passes without us, right? And then this is the offspring, which is what you're counting, what you're measuring. So at time 0, you have 1. So time point 0, x-axis, you have 1. There he goes. Time point 1, you have 2. So x-axis 1, up 2. Time point 2, you have 4. 2, you have 4. 3, you have 8. And Houston, we already have a problem, right? Because this only goes up to 6. 8 would be up there somewhere, right? It's already beyond. And even if this were to go up to 10, 16, you'd be, 64, you'd be way off the screen. And this is where the semi-log paper comes in, because the semi-log paper gives you the ability to calculate, to graph things that are, you can graph things from very small numbers to very large numbers, because you graph things in a log. The axis down here for semi-log paper is still linear. So here's your 0, here's your 1, 2, 3, 4, 5. So that one's easy, right? So you can just label that. The things where it becomes interesting for semi-log paper is when you go on the y-axis, and this is the x-axis, and this is the y-axis for semi-log paper, and this here is a log. This is what it looks like after cleaning it up a little bit. And now this is where the magic happens. So the first thing I want you to look at here is, I want you to look at this semi-log paper. And the first thing I want you to realize when you're looking at the semi-log paper, let's make the laser pointer here again, the pen, is that this looks like this thing down here, this first section here, looks exactly like that second section here, looks exactly like that third. So semi-log paper has a number of cycles, and the first thing you need to figure out is how many cycles you've got there. So in this case, we have 3 cycles, because we have 3 repeating units, right? And I'm going to delete that right away. And so you have 3 repeating units, and the kicker on semi-log paper is that those repeating units, they always represent multiplications, because it's a log. It always represents a multiplication with 10. So your graph starts, your numbering on your y-axis starts with a 1 down here on the first cycle, on the bottom of the first cycle. Then the next thing I want you to label is the bottom of the second cycle. So this is important. This 1 down here, it's not a 0. Students often mess that up and they put a 0 down here. If you put a 0 down here, it won't work. So you put a 1 down here, and then this here is that 1 multiplied by 10. So that's a 10. And then the next step over here is, again, multiply this number by 10. That's 100. And then up here, that's 1,000. Okay? Then we're going to have to figure out the numbers in between. And the numbers in between are not linear. So it's not the numbers actually are where the lines are. So you're not trying to do equal spacing like you did over here, right? Your spacing is off on purpose because this paper basically takes a log for you. So this is the one, and then you just count up just like you would here, right? Here you had 0 here, you have 1, 2, 3, 4, so you just count the lines up. 2, 3, 4, 5, 6, 7, 8. And if you've done it all right, you end up with 9 up here and then 10 there, and that's it. Now, the one where students mess up is the next one. You're trying to get from 10 to 100. So, and you're trying to do the steps in between. If this were a linear, like if this would say 0 and this would say 10, most of you would say, well, the next one's 20, the next one's 30, and the next one's 40, and the next one's 50. But somehow, because this is a funny looking graph, that's not what people do. They're like, oh, this is 11. No, it's 20. This is 20. Just like here, it's all multiplied by 10, right? From one cycle to the next, you multiply everything by 10. This is your 30, 40, 50, 60, 70, 80, 90, and then you have 100. And note that the 50, when you're looking at from the 10 to the 100, the 50 is actually here. So it's not in the middle, right? It's like 2/3 up. And that's because it's a log axis. It's not a linear axis. And you kind of have to rethink how you graph things because it's not a linear axis. If this is 100, you're trying to get to 1,000. This is 200, 300, 400, 500, 600, 700, 800, 900, 1,000. Okay, and then we're all the way up. After cleaning this up a little bit, this is what you get. And now let's go graph these items over here in this graph, in this semi-log, on this semi-log paper. So back to our pointer options and to our pen. All right, so 0 on the x-axis and 1 on the y-axis. So 0 on the x-axis, 1 on the y-axis. This is where this is. 1 on the x-axis, 2 on the y-axis, 1 on the x-axis, 2 on the y-axis. 2 on the x, 4 on the y. 2 and 4. 3 and 8, which is right here. 3 and the 8. 4 and 16. 4 and 16 is going to have to be between 10 and 20, right? And remember how we said that 50 was about 2/3 up? So 16, 4 and 16 is going to be about here. And in your paper that you have, there are lines in between here that you can count exactly the same way how you count the other ones. And I'll go over that in just a minute. 5 is 32. 5 is 32, so that's going to be about here. And 6 is 64, which is going to be about there. And we don't actually have to stop at 64, right? We can go to 128. And I can do you, so 128 is going to be, so 120 is going to be about maybe thereabouts. So 128 is going to be here. Well, that would be 128. Let's say 128 right here. And 128 times 2 is going to be 256, right? So 256 is going to be about thereabouts. Do you see the magic yet? This here is actually basically a straight line. So oops, sorry, if I could draw, I'll clean it up in just a second. So you can actually, without doing the calculation, you can actually expand that straight line all the way to the top and say, well, at about generation 10, we should be at about, 1,000 or so, right? So when we clean this up a little bit, we see that at about generation 10, we are over 1,000, 1,020 something, right? Because we know that the distance to the 2,000 would be, so it's more than that, but and you could put another cycle above it to get to the 10,000, right? Um, so this is how you graph on semi-log paper. Now, to make the move to the actual assignment you have, let me show you the data that you're graphing, because you're going to not start at the corner on the bottom because you're not looking at offspring, you're looking at decreasing numbers, right? So your data looks like this, right? And you're asked to fill in the gray areas here. So I'm going to do this for you for the first couple. So basically how you get to these numbers, you just double this one, because we were smart. We started with 50 dice, because what we're graphing is we're graphing the percentage. So for the population here, this is where the numbers go, and then you just fill in the rest of these. This is exactly the same idea. For the soap bubble data, what you're going to do is you're going to simply count the check marks. So 2 check marks, you put a 2 in here, and then you just take the number from above, deduct the 2 that just died at this generation, you put the number over here. So this is, and when you have nobody dying, the number just doesn't change. And then here, just like with the heart disease and the dice data, you just double the numbers, and that's how you get your numbers. And let's talk about how we graph these. So I created this so that it looks familiar again. Here's the data from the heart disease and cancer. This is the data that you already remember from the time, generation, and offspring. And so this time you're going to start at 0 and 100 on the y-axis. So 0 and 100 on the y-axis. So your first point is right there. Then at 1, you're going to 66. So 1, go up to 60. And remember, this 5, 6 is about 2/3 up. So it's going to be between 60 and 70. And again, your sheet that you have has a couple of in-between numbers that work exactly the same way. 2 is going to be 44. So it's going to be thereabouts. 3 is going to be 30. 4 is going to be 20. 5 is 14. That's about there or so. And 6 is 8. 6 is, there's 9, so there's 8. And then yours goes on a little further, but then all you got to do after that is you put a line through there. And at the very end, you're going to compare the 3 graphs, the 3 lines you made, the dice 1, dice 2, and the soap bubble population, and compare those graphs to the graphs we talked about in the lecture, the type 1, type 2, type 3 survivorship. And that's it.